So it's a pleasure to be here. I'm Matt Bates. I'm from Jetstack. We are a container consulting company. We're very, very focused on Kubernetes. We've been using it for quite some time now. We contribute, we deploy, we train, we do all sorts of bits and pieces. One of the really interesting things that we've been dealing with more recently, I guess, is states. Now, who here wants to run a database on Kubernetes, or who has attempted to run it? Okay, a lot of people want to run it. So I'm ex-MongoDB. I was there for several years. I hope that's a good thing. People like MongoDB. So we've been using database, and actually I can see the benefit of using something like MongoDB on Kubernetes. Just from my background, I've also done a bunch of stuff in data consulting, so I've basically been dealing with databases for a long time, grappling with them, getting them to do good things. And I'm a coder and a big fan of Kubernetes. So what we're going to be covering today is why stateful services should be run on Kubernetes, and there should be no reason why we can't get there. We may not be there quite there yet, but we're going to look at where we can go to get there. We're going to be looking at some of the databases you can run on Kubernetes today, and I'm going to try and sort of identify some of the pain points of running databases. Then we're going to look at some of the building blocks. So we're going to go down and start looking at things like replica sets. We're going to start looking at things like daemon sets. We're going to look at volumes, persistent volumes, so all of the building blocks basically that you need in order to run a database. And again, some of the strengths and weaknesses of where we're at with all of that. We're going to piece it all together, and then we're going to can we do this better? And we're going to look at something called pet sets. I know Kelsey mentioned it briefly earlier. We're going to have a look at that as well. All the while, really, what I want to try and do is show you what's there, what's coming, and also get you to sort of try and contribute some of the things that you'll be able to do. So, who here agrees with this statement? Most people? It's pretty big. It's pretty awesome. I mean, there's a lot of great things about Kubernetes. We're seeing great things in some of our deployments right now. I think the two previous speakers have probably done a very good job of actually substantiating some of that. But, there is always a but, I really want to run stateful containers. Did anyone read this article at TechCrunch? Did anyone see this? And there's a lot of commentary that's a bit similar to this, that actually I don't just want to run Nginx. I want to actually run my full stack on something like Kubernetes. That is, I want to be able to take a database like MySQL, MongoDB, or Postgres and run it alongside everything else in my cluster. So, well, why not? I mean, the question is, why would you want to run a database on Kubernetes? Well, as I said, why would you not? Because actually it's a process like any other. So why should I have to deal with my database in this completely different way to the way in which I deal with the rest of my application stack? I really want to be able to use Kubernetes to be able to manage the entire stack for me. So there's lots of really good benefits that we know from using Kubernetes. We can very, very efficiently use clusters. This is one of the things that Google teaches us, that you can actually use something like Kubernetes in order to get the best bang for your buck. You know, you can use all of the spare compute that you have and use it as efficiently as you possibly can. And that also applies to a database here as well. I might just want to be able to use spare IOPS. I might want to be able to use spare RAM that's kicking around. And actually, if I've got a very clever scheduler, I can do that. That brings me on to scheduling and placement. We need to schedule databases. And actually, there's some specific rules about how we put a database into a cluster, and actually these things are done today by people who do it manually pretty much. If you want to go and deploy a highly available database, what do people do? Well, they work out the zones, they then deploy across those zones, they maybe deploy across regions. Someone is actually manually doing that. But actually, could a scheduler do that for me? Yes, perhaps that it could, and it could do it probably pretty well. You also get this ability for scaling. Again, today, we can elastically scale. So if you take something like MongoDB as an example, you can shard your data so you get horizontal scale out. Wouldn't it be good if I could have a process which was monitoring the database that was able then to scale on demand and perhaps scale back as well? Again, you can do auto-scaling. Has anyone used HPA? So horizontal pod auto-scaling. Anyone used it? I don't know. So you can use it. It's kicking around. It's there today. So how about we extend that to the database? And then there's also consistency of automation. As I said, why should you have your database be any different to your other application systems that you've got? So, you want that real consistency. You want to be able to say, look, I have a deployment. My deployment that has Nginx, but it also has a database. Perhaps even has a message queue or something else. And well, Google do it. Google have been doing it for decades. So clearly, if they've done it, it probably can and should work. So one of the building blocks to actually running a database, of course, is that we need to be able to write data, and that data needs to be able to persist to something, a volume that we can then actually remount. So volumes can be attached to pods, and I'm assuming a lot of people probably here have already used volumes already. Now, the good thing about this is the volume will outlive the lifetime of a container. So that is, if a container were to die inside a pod and the container were to get restarted, that the volume's still there. Yep, it's fine. It's okay. Well, we can attach a bunch of different volume types. So we've got a few there. We've got local volumes. So a lot of people have probably used just the empty directory. That is, the kubelet will set up a directory on the host, give it a unique name. You won't know that. You won't set it. But it will actually go to a disk, assuming you've got a disk sitting behind it. And then you've also got the host path as well. So that's where you can quite specifically tell Kubernetes where on the host that you want the data to live. So you might have a very specific mount point on the host that you want to make available to a container. So both these are available to you already. And there's also a bunch of network volumes as well. So you can attach it to the likes of GCE PDs. You can attach it to EBS volumes, NFS iSCSI cluster. And there's a whole bunch of these things. And the great thing is this is a sort of plugin based. So you can actually, if you really want, go and write your own. And I know Alex, where's Alex? There he is there. Sorry, highlight you. But you can go and see his talk later where he's actually be talking about how you can actually go ahead and write your own volume plugin. And in fact, we actually wrote the one for Flocker, if anyone's ever heard of Flocker or used it. So you can go ahead and use ClusterHQ's Flocker now as a kind of volume backend. And that will give you a bunch of different storage backends that are not yet available in the Kubernetes mainline. So that's going to get us so far. And of course, the important thing to point out there is that the container, so the volume gets mounted inside the container file system. So you can state what you want it to look like on the outside, and also state what you want it to look like on the inside. So that sort of outlives the life of a container in a pod. How about if, though, of course, the pod were to die? For instance, the pod would then to be rescheduled somewhere else. Well, that's okay with a network volume, because actually what really happens is it's just like merely unmounted. And then when your pod gets rescheduled somewhere else, of course, it can go back and sort of reattach itself to a network volume. Not so good, of course, if you're using empty directory or host path, because suddenly you've just tied it to a node, and that node may no longer be available. You may, of course, not even have that disk any longer, or at least in a reconstructible form. So for that reason, there is PVs, or persistent volumes. Has anyone used these yet? Okay, so quite a fair few people. So the nice thing about this is it's an abstraction, lots of great abstractions in Kubernetes. There's another one here where you can basically abstract the storage provisioning from the actual storage consumption, because it's going to realize that actually in lots of organizations, it's not the same people that are actually creating disks and then using them. Typically, you might have a team of people who are looking after your storage, and a team of people, developers, of course, that are then going to go ahead and actually consume it. So this abstraction is a really nice one, and it has basically two parts, main parts to it anyway. A persistent volume, that is, this can be a piece of network storage that's provisioned by an administrator. That's an important thing. And this has got a completely independent lifecycle of any pod. So this will outlive the pod. You can go ahead and get back to this. And we've then got a claim. So actually, when we want to go ahead and actually use a piece of storage, the storage is an object resource, as we'll see, that you can actually put into the system. The developer can then go back and make a claim on that, and then use that claim in a pod. And of course, they can then go back and reuse that claim later at a later date, should, for instance, the pod die for any reason, or indeed they want to use it in another purpose. So yeah, these requests are made by users. Works for all volume types, worth pointing out here, apart from those with the local volume types. So what does this look like in terms of a life cycle? Well, very first point here is we basically make the persistent volume. So you can see here what I've got is an example of a PV that I've created for a volume that is going to back a MongoDB instance. This is going to be a bit of a running theme. I'm probably going to use MongoDB examples throughout. And then also I can state some attributes about what that kind of storage looks like. So at the moment, it's relatively limited, but I can state a size. In the future, you can imagine being able to state more attributes about the storage. And that's kind of up for discussion. There's some ideas around actually being able to add more attributes that you can then use when wishing to bind to that PV. There's then the persistent volume claim. So this is effectively where I'm making a request for storage. my storage goes into a pool. I'm then making a claim on that storage in the pool. So in the case, this is what you can see is I'm basically giving it a name or giving it some metadata. And as you can see there, at the very bottom there, I'm actually requesting 10 gigs of storage, effectively. You've got a controller which sits in the background, which is basically reconciliating all of these volumes and the claims and matching them up effectively. So very quickly, after creating the volume, creating the claim, this will become bound. And then I can go ahead and actually use it. So as you can probably see here, what I've done is I've basically replaced the volume where I might have been previously using the AWS EBS volume. I've actually replaced it with a persistent volume claim. So it's a kind of volume type, if you like. And I'm basically saying, look, go ahead and use that claim. And in this case, mount it to /data/db. And I can then just go ahead and use a sort of relatively standard MongoDB container, which will rediscover this. And this kind of all works. I'm not going to run a live demo. I haven't got huge amounts of time, but this does work. I demoed this last week. And it seems to reattach very well. So we can sort of get so far with volumes and PVs. And actually, there are a whole bunch of databases that you can probably already find out there on the GitHub on how to run database on Kubernetes. So the likes of MySQL, Elasticsearch, Cassandra, Rethink. Has anyone deployed any of these things using some of these examples? Yeah. So there's some great things already out there. They use a variety of different techniques. Some of them, interestingly, are not PV backed. I actually had a quick look at some of these recipes behind these. Some of these don't use PVs as an example. They're just using volumes. Some of them, in fact, are not even using network-based volumes. They're just using the local ones. So you might have an interesting time if you were to, for instance, lose all of your instances. I'm not quite sure where that would go. And there's also some recipes around for distributed storage as well. So this is mainly about sort of client access to storage clusters like Ceph and Gluster, for instance. And there's a whole bunch of other ones which are arriving as well. There are some thoughts about running Ceph and Gluster in containers as well, and we'll get to some kind of the building blocks behind that. So yeah, a bunch of good things already out there. One of the ones that I wanted to focus on, or at least one here that I wanted to focus on, is Vitesse. Is anyone here heard of Vitesse? So effectively, this is MySQL that's used at YouTube. This has been in production since 2011, integrated into Borg, obviously in the very early days. It now runs on Kubernetes. And they've actually been doing a lot of work to actually get it running much more natively in Kubernetes. So you've got MySQL. I believe it's also based on MariaDB as well, so you can sort of bring your own. Does sharding, horizontal, vertical scaling, does master failover, and it kind of always works out of the box here as well. So I think if containers have been used in order to back something like Vitesse, and it powers YouTube, and you can see here, I think YouTube's user base has increased like 50 times, like to 1 billion users in the time, then clearly this might be a way of doing it. So looking under the bonnet here at what it kind of looks like, well, effectively you've got multiple containers which run in a server pod. They've got something called the VT tablet, which effectively is like a smart proxy, which sits in front of effectively MySQL. This is all backed at the moment just with kind of ordinary pods which use empty directory. So it has a very interesting way that it actually just pulls its snapshots down from, I believe, Google's cloud storage or NFS. So it'll basically take periodic snapshots, put those snapshots out to storage, and it can then use those in order to effectively bootstrap new nodes as they come online. So this is a pretty good thing. It doesn't use any replication controllers yet, or replication sets, as we'll get to, so just individually managing individual pods. But some really, really nice ideas here. And actually, they are contributing some of the ideas that I'll kind of outline a little bit later. Okay, so some of the building blocks, if we were to actually take a database and want to run it on Kubernetes, we obviously looked at volumes. That's one part of it. The other part of it is actually running replicas, because of course, with a database, we want to run multiple instances, not just one. We want to run a whole raft of them in a cluster for sort of horizontally scaling, but also for redundancy as well. So everyone, I'm sure, is probably pretty familiar with the replication controller. It has changed name. It's now the Replicas set. So be aware of that in 1.2. So effectively what this does is it kind of cookie cuts based on a pod template. That's really what we're getting. We're asking for it to create a number of replicas, and it will always ensure, or at least the controller, will always ensure that those exist. So it's always doing that kind of reconciliation. The thing with replication controller, though, is it's always creating something that's the same, hence the cookie cut. It's always creating something that has effectively the same image. So it's actually really, really difficult to sort of say, well, actually, I don't really want my other pods in this set to have, for instance, the same identity, or indeed the same volume that backs it. I actually want it to be different, and of course in database land that's pretty imperative. We want it to sit on different nodes, we want it to have different host names, we want it to have different volumes. That's of course the reason that we're making this redundant. So the only attribute that differs, as I said here, is that effectively the name. I think that comes from the metadata.name, and if you choose replicas, you get unique names as well. And you probably saw in the demo by Kelsey that those names were pretty unique. They were generated. Pods also have no stable network identity other than the IP that they're given. So each IP, of course, or each pod, will have a unique IP, but then there's no unique sort of network identity or stable network identity. That's a bit of a problem, particularly having no fixed and predictable host name that we can use, or at least that we can understand, that's going to last past pod failures. And so what this is really, really good for, as we probably can see, really, is just kind of shared nothing, zero coordination systems. These things that are basically very, very parallel. I think it's described as embarrassingly parallel. So things that you can actually just put out there, you can have lots and lots and lots of these things. They all look exactly the same. Effectively, you can load balance across it. That doesn't sound particularly good for a database. So another thing has arrived, which is this called daemon set. Anyone had a chance to play with this? Few hands in the room. Okay, so this is a particularly useful thing. I think it arrived in 1.1. It's now GA, I believe, in 1.2. So this enables you to effectively take a daemon that you want to run on all nodes in a cluster, or indeed a subset of nodes. So typically you might want to use this for things like monitoring agents, logging agents. I've been using it just recently for running things like FluentD instances, for Datadog instances. I think Datadog's got a recipe for running this is a daemon set. So effectively, everything, this is good for kind of per node services. So how about for stateful services? Could you use daemon set? Would this be a kind of good match? Well, in some respects, yes. You could actually effectively label your nodes. So I could actually say, look, I've got a node. It's going to have databases. I'm going to add a label to that effect. And then you could use a label selector in the daemon set to say, when you land these processes, when you land these database processes, make sure they land on sort of certain machines in my cluster. And you can sort of almost get to a point where you can sort of do like an anti-affinity. You can start sort of spreading your database across your cluster. It was also pretty good, of course, because nodes have fixed identity. I mean, they have a host name. You can always address them. They don't change. And they have persistent disks attached to them. So this actually gets you a little bit further than the replicas set. But if you ask me, this feels like too much like a pet still. We're still having to have this massive tight coupling between the pods that we're running and the nodes. We're actually having to think too much about running that database process on a node and putting and landing it. So that actually almost feels like a bit of a kind of Kubernetes anti-pattern. Really, what we really want to do is let Kubernetes do the hard work of actually the scheduling and the placement for us. And I don't think we really get that here. We're getting, it's a little bit too manual. So, okay, once we've got a set of replicas running, one way in which we can give it a stable identity, as probably people know, is to front this with a service. This, again, is another abstraction in Kubernetes, a very neat one because it gives us a stable identity that we can always use. In this case, it gives us a VIP, virtual IP. So in the case of something like MongoDB, I can have a bunch of nodes running. This might be Postgres, this might be Redis. A bunch of these running in the background. These have all got IPs. Of course, these pods can die. These pods can come back up. They can have new IPs. They're completely fungible. So we shouldn't rely actually on their IP, nor should we indeed rely on its identity. So what we can use as a service, the service, as you can see from Kelsey's demo earlier this morning, really easy to create. We can expose it. We can get it to select pods based on node. So we could do this for MongoDB. And what we would then do is basically round robin requests through the VIP to the backend pods. But that's actually not going to be particularly appropriate for something like MongoDB, of course, where in fact we can't just talk to any node, or at least we could if we kind of want, we were happy with just reading and we were just happy with eventual consistency. We could do that, of course. Then what we really need to do is actually, of course, talk to the master. We don't actually want to talk to a secondary. We want to talk to a master so we can do both reads and writes. So one of the things that you can do, worth pointing out here, is you can make a service headless as well. So rather than actually just getting the VIP, you may not want the cluster IP at all. You might actually just want to know all of the IPs in your set. Then you can make just a headless service, and then you can use DNSA records, and you can use the API. You can go back to the API and say, tell me what my MongoDB replica set looks like and what its IPs are at this point in time. And of course, that could change as well. But as we know, and I think I've already kind of alluded to it, a lot of these systems that we want to run, or these distributed systems, they all look a little different. I mean, these things are all not created equal. They all have very, very different ways in which they operate. So a couple of examples here. One is leader-elected quorum. So if we're using the likes of MongoDB, Zookeeper, etcd, we've got a bunch of nodes. They form quorum, and they will do failover on our behalf. So that means we actually need to obviously make sure that we're talking to the right node. It's got its own behavior. It elects itself. Kubernetes is not involved in that process. It's actually doing it itself between the pods. You've also got things like active-active, multi-master. So the likes of Galera here and Elasticsearch probably fits into that category. You've got other classes, of course, with the likes of things like Cassandra or decentralized quorum. So actually, it's quite tricky in Kubernetes to build something that's going to be able to understand all of these different distributed systems and all of the various nuances that are attached to these as well. So perhaps it's really tricky and shouldn't be done. So one of the ways that you can use some of these things that I've just been talking about, so the likes of volumes, the likes of services, is you can actually today get something like MongoDB working. It's a little clunky, so bear with me. So what you can actually do instead is you can basically have a service and a replication controller per instance. Because what this gives you, and as you can probably see here, it gives me the ability to have some fixed stable network identity for the pod. So it doesn't matter now, for each of the replicas in my set, they can come, they can go, their IPs can change, but they can have a fixed IP with the VIP. And you can probably see here, I've got a couple of VIP IP addresses that are there at the very top. They're doing label selection to the pods. Pods are actually running in replication controllers, so should one of those come down, then it will be brought back up. And I'm also using PVs and PVCs, so when they do come back up, they're always going to attach themselves back to the disk that they had before. So this sort of gets us there. I mean, it's not quite as elegant, as just creating a single YAML that describes my distributed system and for it then to go off and do it for me. I've got to go ahead and kind of script this on the client side, and has anyone done this? Yeah, so a few hands already. So you can sort of do this. You can just go ahead and write some script code that effectively will for loop round the number of replicas you want to create, and you go ahead and use the API or use kubectl. So you actually go and create the pods, create the replication controllers, effectively almost like kind of use templates, parameterize templates, and spew out the necessary YAML. You can also use things like headless services, as I said, for doing things like discovery as well. So you can put another service that wraps all of this, that then matches all of those nodes, so that, as I said, you can discover the pods that are inside your set. But you can probably realize here, what we're actually getting to is a position where we've basically got lots of resources to manage. No longer have we got the single YAML file. We've actually probably got, potentially tens. Let's say you're running a multi-shard, multi-replica set. You end up with actually having a very, very large set indeed. And it's actually pretty difficult to manage now, because imagine trying to do an upgrade. You want to upgrade from like one point version to the other. It's not as easy as doing the kind of deployment that we saw from Kelsey earlier. You've actually really got to do the deployment on each of your replicas that are running, or each of your shards. This is a little bit tricky. Not really what people expect. Also, you get pretty unexpected results. This is my time with doing it. So I've been trying to get MongoDB to run pretty well. I've actually been finding that you get some really unexpected results, because what happens, it kind of all works when you set up the set. It all seems to function as you'd expect it to. But then when one of the pods dies and perhaps gets rescheduled onto a different node, has of course had a different identity, you get really unexpected results, because something like MongoDB doesn't expect that, because internally to the pod, the hostname has changed. Externally, of course, it might still be using the service, but actually internally the hostname has changed. And then once it reports itself back to the other nodes in the set, it says, I have no idea who you are. This is not going to work. So you get to a point where you've actually then got to remove that stale member and then put something back in again. So this just feels like much more harder than it needs to be honest. So that's probably not a great place to be. So kind of looking ahead, what we've got actually coming in 1.3, at least I think it hopefully will arrive in 1.3, is this ability to create pets, so sets of pets. Because pets are still important, as we can probably see with databases here. We do actually have a good case for them. And the proposal there, 18016, probably worth reading. There's also a proposal for, I believe, nominal services. It's got a much lower issue number, 260 maybe, I don't know. It's one of those. Lots and lots and lots of discussion in this area, so I highly recommend you have a kind of flick through. There's lots of good opinion. But eventually what it's got to is a position where there's a resource that will be created for a pet set. Basically what that will enable you to do is represent pods that, as I said here, and I've nicked the quote, individually distinct, but each individual. I think that's a good way of describing it. There's also another great analogy that's actually been brought out, and you kind of, if you read this, basically it's this idea of basically having multiple coloured goldfish. If you have the blue goldfish, the green goldfish, and the blue goldfish, if one of those was sadly to die, in order for no one to notice, you'd need to go back and replace the one that died. So let's say the blue one died, you need to go and replace the blue one. It has its identity, it needs to be the same. No one would notice if you were to put the blue one back. So I think that kind of describes this problem quite well, in that if basically you've got lots of database instances, you want to bring back what was originally there, effectively, with a similar identity, similar disk, so that the cluster can sort of happily carry on again. This idea here is that you can create and maintain identities. You basically ensure that you've got a set of identities, though those identities can only, of course, have one pod effectively that can use it. And there's a bunch of supporting resources. So this also talks about being able to support things like volumes as well, that will actually go ahead and sort of attach itself to the pod. Okay, so what it proposes specifically is sort of basically creating like this parameterized template. And I think Gareth's talking right now actually about how you can use sort of config management to do something similar. Effectively, you could take a piece of your own code or indeed some config management to spew you out these kind of parameterized templates. That's effectively what's being proposed here, that there will be a way of informing Kubernetes of the effect of your template, and then there will be means to control that template in order to inject in the various parts of the identity. So you, for instance, could control the hostname. As an example, I want Mongo 1, Mongo 2, Mongo 3. I then want to be able to control the names of the volumes. And again, you can go ahead and give it that pool of identities that you control and manage, and that it then pulls from. And there's a couple of important things here. Obviously, you need to be able to identify them clearly. You need to be able to give them predictable names. This is particularly important. You also want to be able to set environment variables so that those environment variables can be used internally. And also, you also really want to inject in the size of the number of replicas as well. Again, this is pretty important when you're bootstrapping, because you're going to need to know the number of replicas, but perhaps to do something in order to get that kind of be the case. So look at 18016 even, sorry. There's a lot of good discussion there about how this will take place. I think there's a handful of ways in which it's been suggested. I think there's at least probably 4 or 5 different ways in which this template might look. It's indeed, the proposal's not even been merged yet, so this is a good opportunity to get in, respond to the proposal, and eventually it will get to a point where there is actually something for implementation in 1.3, and this will be actually a better way of doing this, much better way of doing this. Okay, one of the things that actually has already arrived, though, which I'm really glad about, and this is like a little small start in 1.2, is this one. I think it's 2688. I hope these are all correct as you navigate to them. But effectively, this has already gone in. This is the ability to generate effectively DNS and to actually specify the hostname and subdomain of a pod. So you can actually basically override the behavior that is the case right now. This is really, really useful. So normally a pod's name is a hostname, is its name, but now what you can do is you can set a hostname and a subdomain annotation. Very, very small snippet there that probably shows you how you can use it, but effectively you just use it as you would any normal annotation. So in this case, what I've done is I've annotated it with the name of the host, Mongo 1. I've also given it a name of the set, which is going to be replica set 1 in this case. And what will happen is, of course, the host name will get generated, and if I was to cat the host name, I'd be able to see a fully qualified domain name. A bit like the following: Mongo 1, RS1 default, assuming I'm in the default namespace, service cluster local. So you'd actually get something that's predictable, that you can then rely on and use inside your cluster. If you're also running SkyDNS, I think probably a lot of people do, in my experience, and you're using that for internal service discovery, and this, if you have a headless service, and it matches the name of the subdomain, what it further goes ahead and does, and actually creates an A record as well for you with that fully qualified domain name. So what we now get is the ability to control the host name, and that's really, really useful because I think I pointed out when I was running MongoDB back in this example a few slides ago. Oops, we've been running it here. The problem you get, of course, is if the pod comes back, the pod comes back with a different host name. You don't want that. You really want to be able to control it. So in some of my tests so far, what I've done is I've already managed to set the host name as per these annotations, and actually when it rejoins the set, it actually knows that what it was before, and it carries on. And in the case of MongoDB, it kind of catches up on what it's missed out effectively. So we're getting like much closer. I've still got the problem that I've got to manage all of these individual resources, but I think if you look at PetSet and look at the proposal for PetSet, the idea is that there will mean that I can actually have a single template rather than the kind of some of the hand cranked code that I've got at the moment. So we're kind of like we're getting closer. We're not quite there. We're getting there. I would certainly take a good look at PetSet. I'd also take a look at some of this stuff that's come out recently. These are just annotations at the moment, so that is to say, and correct me if I'm wrong, this will be a little bit experimental, so your mileage might vary, but in the future, of course, that might become sort of promoted to a field or something where you can actually do it more formally within the API. A couple of other things that I think are really worth looking at. And again, these things have kind of appeared in the 1.2 timeframe. Certainly, proposals out, and things will appear in the later versions. Are around scheduling, because with a database, actually, if I was to deploy it to Kubernetes, what I want to be really sure is that actually it's going to spread, for instance, my nodes across zones. If I'm running in AWS, what I really want is each of my replicas in my set to belong in each of the zones. Now, there are some things already built into the scheduler which have already merged in Kubernetes Lite. Anyone heard of Kubernetes? What a great name. So Kubernetes, it's kind of coming. This is for doing cross-cluster federation. But there's a Lite edition which has already appeared, which enables you to run effectively clusters across zones. So imagine running it in zones in AWS. The scheduler already has built into it some logic that will enable you to spread by service. So if I had a MongoDB service, as an example, I could have a Postgres service, any other service. If I wanted to ensure that there was a good spread, that's actually already built in. As long as my service exists first, and then I go ahead and create my pods, actually the scheduler will do a good job, alongside all of the other predicates that it has to bear in mind, to actually spread those across it. And actually, from my tests, it's done a pretty good job. I've said, look, I want to land Nginx on each zone across AWS. I want to land MongoDB in each zone across AWS. It's actually done that for me pretty well. But there are some newer kind of ideas coming around node affinity and anti-affinity. So that is, if you want to be a little bit more specific and you want to be able to be almost like a bit more granular in the way that you describe these affinity rules, then you can begin to do that. So in 1.2 as an alpha, it's probably worth underlining alpha, bolding it, and we basically get an annotation which enables you to describe the rules for both affinity and anti-affinity. Now, in the case of a database, of course, we're interested in both, but particularly more interested in anti-affinity. Like, actually, we want to spread. We want to spread by zone. We want to spread by region. We want to spread by rack. Whatever it might be, we want to ensure that, of course, this database is not going to be centralized to one single place. So, as an example, one of the ideas, and again, this is from the proposal here, is scheduling a node with an SSD in zone X. Of course, that's more based on affinity. So you can be very specific about where you want this to land. The scheduler will take that constraint and bear that in mind when it's scheduling. And there's a couple of ideas here, both these annotations. So required during scheduling, ignored during execution, and then preferred during scheduling. So this idea that basically at schedule time, it will take a look at all of these rules that you've set, try and meet them as best it can. In the case of required, of course, it's absolutely required. In the case of preferred, it will do its best job in order to land it on the right node. And at the moment, it's ignored during execution. What that means at the moment is that it will not reevaluate that later. At least that's my reading of it. That, for instance, if you were to make a change to a label on a node at some later date, it wouldn't then go ahead and sort of work out whether those pods need to be evicted and moved. But anyway, it's a good kind of step, because it means you can start doing all of the things that are actually really important with a database system. All the things that we do today. I want this to land, as I said, on the SSD node. Why? Because it's faster. I also want it to land on a particular node as well. One thing that's probably also worth shouting out, and I won't talk about it in too much detail, not least because I need to read more about it as well, are also taints and tolerations. Has anyone read about taints and tolerations? It's like buried in sort of GitHub. You've got to kind of dig your way through it. But this is the idea that you can basically almost like dedicate nodes or subset nodes to particular purposes. So administrators can say, no, that's actually my very high performance CPU box, and that's only going to be used for particular pods. So that's much more about being able to restrict it on the administrator side rather than here. This actually is a request that you can, of course, make at the time of creating your pod. That at least feels to me the differentiation. So look at that as well. That's at proposal stage. That's certainly not implemented. Probably worth pointing out that there's actually a load of node information that's already being kind of annotated, so you'll get the hostname as an annotation. Interesting, you also get zone and region now. I don't know whether anyone realizes this, but if you're using it in AWS or GCE, what you will get is an annotation that you can use with zone and region, which is really useful if, for instance, you're using the node selector, which is kind of the current way of doing kind of node affinity and anti-affinity. So you can say, for instance, like, I want this to land very specifically in a region. I've had to do this on occasion to make sure things match up and get themselves to the right place. And there's also instance type, which I think is pretty neat as well. So you can start using that when making a scheduling decision. So make sure you land this on a particular node. Maybe you're paying for high CPU instances and you want to land it on those instead. So these things are all available, and you can kind of use them. Oh. That's good timing. So you have a look at these things. They're pretty useful, and I think they're going to be even more useful when you're getting to being able to schedule databases. I'm certainly very keen to use some of these things quite soon. The other thing that's probably worth looking at... Oh, and it's all not working now. Hang on. There we go. Good. Back to the keyboard. Another thing that's also worth looking at is into topological affinity as well. So this is about saying, actually, I want you, when scheduling, I want this to land on a pod that's running some other pod. Again, this is really useful in database land because, for instance, if you're doing some kind of job processing, and again, job is a new thing that's kicking around. I think it's now gone GA in 1.2. If you want to run some kind of computation, you of course really want to run that computation on the node that has the database. What you don't want to start doing is just landing it anywhere and then having the cost of the bandwidth and the latency potentially. So again, this could well be very useful. Again, at proposal stage, don't think this is kind of available to use yet. It's not, but it's certainly available to comment and contribute to. I again think this would be pretty useful. Okay. I've just let the stopwatch on 38 minutes, so just to summarize. So Kubernetes supports a wide range of data volume types. I know Kai from Cluster HQ is going to be talking about using data volumes and all the various different types of them. So head along to his talk if you want to find out a bit more about the different volume types. I believe there's a couple of other talks which are also going to be talking about volumes. So if you're really interested in that side of it, head that way. There's a whole bunch of things that I can talk about in the time. Considering using PVs, they outlive pods. This is particularly important. Just get your head around the PV lifecycle. So that is creating a PV, creating the claim on that PV, and then being able to use that claim in your pod. That's obviously a pretty awesome way to go for databases. There are ways to run a lot of databases. I've kind of cited the example of MongoDB. I believe there's a Postgres talk coming up later. Yeah, indeed, the guy in the front row is going to be doing that. I'm really interested to watch that as well, because I think some of these ideas probably might be similar. I'd be interested to know how, for instance, things like master failover work as well. Client-side templating is the way to do it at the moment, or at least one way to do it. And if you look out there at the various open source projects, you'll probably see them stamping out this kind of thing. It gets us so far. Early pet set stuff is really cool. So as I said, it's a small change, but it's a really useful one. It means that you can start doing things you can do before. Pet sets will be getting better. I think there's going to be a charge on that development, probably in 1.3. I've got a nod in the front row. So and there's a bunch of things around scheduling as well, which again I think are really quite awesome, because you will be able to run distributed systems kind of properly, not sort of in a kind of hacky way, which I guess is the way you do it now. Recommended contributing feedback. So there's a bunch of links. I'll make these slides available, so just follow them. They generally tend to link to issue and another issue, so you sort of follow it. But it's really worth reading. There's some great people contributing to this, from various different companies who are involved. So yeah, make sure you contribute feedback. Lots of real-world experience. This kind of counts because you are the guys who already run these systems at scale. You've probably got lots of lessons that you can bring to bear, and write some code as well. I mean, pull requests are awesome, and I think we're planning to do some of that ourselves. That's me. I'm from Jetstack. Probably worth noting we are recruiting, and yeah, follow Twitter. We also do a meetup group as well in London. So if you're interested, join meetup.com/contain. Cool. And I've probably run out of time. So if you've got some questions, come and find me afterwards. Hope it's useful. Thanks.